Hey everyone, welcome back. In this video, we're gonna go over chapter 5, time series and their components. Basically, we're gonna learn a formal model called decomposition. So in this model, what we do is we decompose each component of the time series, forecast for each component separately, and then put them together as the overall forecast for our time series. All right, let's get started. First of all, let us review what components a time series may have. Earlier, we learned that there could be trend, and we will denote it with letter T. There could be cyclical. We will denote it as C. The cyclical is the up and downs over the long term. That is at least a couple of years. And there could be seasonal component denoted by S. That is the up and downs within a year usually. And lastly, we also want to add the last component, the irregular I, or we can say it is the random error. Random error. Okay, so 4 of them. And how do we put them together? Well, we have 2 models that we can use, additive model and multiplicative model, all right? So for additive model, we just assume every component are added together. And in the second one, we assume all of the components are multiplied together. And each of the model has its own application. If you take a look at the right-hand side, you will see 2 graphs, right? On the top, you will see a graph with repetitive patterns over time. What you would notice is that the range of the repetitive pattern, right, is quite constant. That is, we would say the variation for the up and downs is pretty constant. It's not increasing or decreasing. Now, if you look at the bottom one, you would notice that there's still up and downs, the same pattern repeats itself, but you would notice that the variation is increasing as time goes by, right? The up and downs become more dramatic towards the end. So for the second situation, we will be using the multiplicative model. And for the first situation, we'll be using the additive model. Now in practice, a lot of the times, the data will show somewhat similar pattern as the second one. It doesn't mean it has to be variability increasing with level. Sometimes it could be decreasing with level, or sometimes it could be increasing then decreasing. So overall, as long as the variability is stable, we use the additive model. When the variability is changing, we're gonna use the multiplicative component model. The task of decomposition is really to break the data, which we can also call it variable, but really we're breaking the data into the components we just mentioned, the trend T, so trend T, cyclical C, seasonal S, and irregular I. So we want to separate the data into these 4 components, okay? And to me, honestly, I think this is quite fascinating and interesting because when we talk about data, right, a time series data set is really a couple of numbers or a series of numbers collected over time. It's interesting to see how we can just tease out 4 components from the series of numbers, and we're just relying on the numbers themselves. Okay, we will need to study each component in much more details than before. Then we will be able to tease each component out and then put them together. We'll start with the first component, trend, because this is the first one that we can easily identify within the data. Okay, So we start with linear trend, and a linear trend is basically a straight line used to represent the data, or a straight line fitted to the data, okay? And the straight line is specified as the following. We have t, capital T hat, equal to B0 plus B1t, right? So actually, what you see here is what we call simple linear regression model. You should have learned this in your statistics course. If not, don't worry too much, because in chapter 6, we're gonna learn regression in much more details. And that's actually the reason I decided not to include this in the review in chapter 2. But I would like to briefly introduce it so that you know how to use it. For the linear trend, the big T, of course, represent the data, right? Our time series data. B0 is the y-intercept, and B1 is the slope. We would like to use the data to identify B0 and B1 so that we can replace them with actual numbers, and then we can do the forecast using the trend. Now, the last item, T here, the small case t, the lowercase t represent time, and T will take value from 1 to 3 until all the way to the total number of observations, okay? Several things you need to know about the linear trend though. Number one, it really mimics the data well, because the data will include not just trend, but also cyclical component and seasonality. If you use a straight line to represent the cyclical and the seasonality, then you are looking at a disaster. There's no way this linear trend can mimic those two components well. However, the linear trend does provide us some indication of the general direction, especially if our interest is to ask whether our revenue is increasing overall or decreasing overall. So it does tell us in general where we are heading. We want to study linear trend also because we want to remove the trend if we want to study the seasonality in more details. If our focus is to look at the short-term variation, which is seasonality, then we do want to take away the linear trend so that we don't get confused with it, right? So in order to identify B0 and B1 and then to replace them with numbers, we will use a method called least squares method, okay? I'm gonna defer the discussion of this method for much later. As of right now, what you need to know is that the y, which actually turns to be t in our linear trend, is the time series data. And we call that the dependent variable. The x, which is t in our model, is called the independent variable. So basically what we're saying is that our time series data change because time change, right? Okay, so that's the idea. So in other words, our time series data, the value of the time series data depends on the time, okay? And of course, when we pick the value for B0 and B1, we want to make sure the values we picked will make the straight line as close as possible to the actual values. Let's take a look at an example so that you can have a better idea about this linear trend. So it says here, data on annual registration of new passenger cars in the United States from 1960 to 1992 are collected. We first fit a linear trend, basically a straight line representing the general direction of the data, okay? So Minitab will allow us to do this kind of analysis very easily. On the left-hand side in the graph, this is the output from Minitab when you conduct trend analysis. So right now, I would like to head over to Minitab and show you how we can obtain the linear trend, which is the straight line represented by the red dots. So here's the mini tab. The name of the data file is new passenger car. There's only one column with the number of registrations. So what we want to do is the trend analysis. So we go to stat and time series. Trend analysis is the second item on the list. So click on it. And the variable is registration. Now you will see that we have several options in terms of what kind of trend we want to fit. We will by default use the linear. And then if we decide maybe the data, some other trend is more appropriate, like later on, we will be looking at quadratic. You can click on quadratic to fit a quadratic line. So let's do the linear as of right now. And also, if we want to do forecast, if we want to use the trend to do forecast, we can click on generate forecast and put the number of periods we want to forecast. Let's do not do that right now since we don't need it. So also, we have the storage option if we want to find the fifth, which is again, which is just the focus. And we can also get the residuals. Not for this time. Not for this time since we haven't discussed those yet. So just click on OK. And we will see right below the basic information, the graph showing us the original data as well as the fitted trend. And you would notice that we do have the linear model for the trend. And this is exactly the same graph we just saw on the PowerPoint. Let's go back to the PowerPoint and continue our discussion. Okay, let's look at the linear trend in a little bit more details. Number one, what I see here is, although we try to put the linear line to be close to all the observations as much as possible, we can still tell it doesn't mimic the pattern of the data, right? We see big up and downs in the data, but for the linear trend, it's just going straight. And somehow, if I look at the general pattern of the data, I might suspect that a curve may work better. So that's the pattern I see. And this curve actually will be closer to a lot of the observations than the straight line, okay? And in order to get this curve, we can consider other non-linear models. So linear apparently is reserved for the straight line. So non-linear is a term we sometimes use to describe a curve, okay? It could be a quadratic trend right here, or it could be an exponential trend. Next, let's look at how we can use the linear equation to focus the trend. And we focus the trend for a couple of reasons. We focus the trend to see where the future values are going. Is it going up or going down? We also focus the trend, then we can tease out the trend from the time series data, and then we can move to the next step to identify other components. So the trend forecast is based on the linear equation we just obtained. T equal to 7.988 plus 0.0687 times the small t. Okay, and our data ranges from 1960 to 1992 with 33 observations. We do need all of this information if we want to forecast one step ahead, meaning we want to forecast for the next period that is not within our data. Let's start from the first observation, okay? For the first observation, the lowercase t will take a value of 1 because that's the very first observation, which represents year 1960. And the trend is given by the original equation. We just need to replace the small t with the value of 1 because t equals to 1. And the answer is 8.057. For the second period, the lowercase t is equal to 2. So all we do in the linear equation is replace that lowercase t with 2. Go ahead, do the calculation, and we got 8.1254. We can continue this pattern for all other values of t. And in particular, if we want to predict outside our data, that is, if we want to predict for year 1993, which is the year right after where what our data cover, we call that one step ahead. Okay, so we're forecasting one step ahead. Then the lowercase t will take a value of 33 plus 1 because we've already got 33 observations. And the very next observation will be 33 plus 1. So we will replace the lowercase t with 34, and the answer is 10.324. Okay, so that's the way we forecast trend using the linear equation we just estimated. As I mentioned, we could also fit in other trend. One particular example is the quadratic trend. It's non-linear. It shows a reverse shaped curve. And we somehow identified maybe this quadratic trend can work better than the linear trend for our data. So for the quadratic trend, if you look at the left-hand side, that's the output from Minitab. I do not intend to go back to Minitab, but basically you're following the same step. The only difference is instead of picking linear trend, you want to click on that quadratic instead. But look at the output from Minitab. What we can tell is the quadratic trend fit the data much better. Especially this is verified by the forecasting error because MSD for the quadratic trend is only 0.89 and MSD for the linear trend is 1.3. So apparently there's a much higher forecasting error with the linear trend. This is expected. All right, although we can say quadratic trend fits the data better, but the question arises is where exactly is the curve restriction heading? Because the quadratic trend will predict that curve restriction is gonna decline after our first observation. Because the quadratic trend will predict the curve restriction will decline continuously and that the over direction is going down. While the linear trend will predict that the over direction is going up. So which one is right? Which one is more appropriate? Well, at this point, we can't just rely on the model. We're gonna need to combine several things. In particular, this depends on the situation. We need to analyze where we are, what we're looking at, and even sometimes use our own judgment. This also relies on experience. The more analysis you do in forecasting, the better you can tell. So to me, if I look at the original data, I would say it shows there's so much variation over years. It's hard to say that the curve restriction will decline forever. Then maybe at some point the curve restriction will go up. However, just based on the trend, we can't tell whether it's going up in the very next period or it's going up after a couple of periods. And we do need to look at other components to better forecast for the next period. Okay. There's another trend called exponential trend. It's kind of the opposite of the quadratic trend. The quadratic trend is showing a reverse shape, and exponential trend showing the other way, right? As you can see, this is a quadratic trend fit to data for salespeople. So basically, we're looking at the number of 6 people for a particular business. And as we can imagine, as business grow, they will need more salespeople. At the beginning, the exponential trend can fit the data well, because when a business starts grow, salespeople grow. We expect that. However, the problem with exponential trend is towards the end, right? We don't expect salespeople to grow indefinitely. We don't expect salespeople to grow so quickly that by the end of the 9th period, we are already at 120, while at the very beginning, we're only looking at around 18 salespeople, right? So that just tells us sometimes exponential trend may not be realistic for some situations. Now, when we go to decomposition Minitab, unfortunately, we can only use the linear trend. That's the only option we have. We could do all of these different trends in trend analysis, but within the big model of decomposition, linear trend is the only option. So I'm gonna stop my discussion of other trend here and move to a few cautious notes for you. When we fit in trend, we do rely on some assumptions. And for these two assumptions, sometimes they satisfy, sometimes they may not satisfy. The first one is that we have correctly selected the trend. Well, that's a big assumption, right? There are times we can easily tell the trend is not appropriate. There are times we may need to rely on other diagnostic analysis to tell us, well, you know what, maybe the trend is not appropriate. The second cautious note or assumption is that since we are fitting the trend using data in the past, we're gonna need to assume that data in the future will be still similar to the past. That is, we don't expect huge dramatic change of data pattern in the future. Otherwise, the trend that is appropriate for the past will not be appropriate for the future. Okay, as we just discussed, in terms of picking the trend, and actually a lot of situations in economic forecasting, judgment expertise are critical. It may rely on personal judgment. It will rely on a person's experience, and that's why sometimes we rely on experts to conduct the analysis. Lastly, we do have some criteria that can help us to pick between the trends and also other analysis. We have the AIC and BIC criteria. AIC and BIC criteria are widely used in a lot of other areas. However, these two are not available within decomposition, unfortunately, in Minitab. So I'll just list them there as FYI. All right, so assume that now we are able to identify the trend and tease out the trend. The next component we can look at will be the seasonality, okay? And seasonality usually can be weekly, monthly, or quarterly. In particular, we see monthly and quarterly data quite a lot. So the seasonality is not something that you always want to remove. The seasonality can be useful when you want to look at short-term implications, especially you want to look at what happens in the next quarter. You want to look at the fluctuations within 1 year. And in that case, you want to study the seasonality very carefully. In decomposition and actually overall in economic forecasting, we have seasonal indices. It's a very neat set of data that will allow us to capture the seasonality within a time series data. Okay, I will explain the seasonal indices within an example instead of talking about the concept right here. The other thing I want to point out is that the way to obtain seasonal indices involves quite several steps in terms of the calculation. And I do not intend to go over these steps. I honestly don't think it will provide much benefits at this level. So we're gonna skip that. And what I want you to carry away from the discussion of seasonality is that you know seasonality is useful and important, and you know seasonality can be captured by seasonal indices. Okay, we will be looking at seasonal indices in the example later on. And therefore, we have two more items left, cyclical and irregular variations. These are the last two we can identify from the time series data. After we identify trend and seasonal indices, we can remove the two. Then what we have left will be the cyclical C part and irregular I part. And these two can be easily identified by using moving average method. So there you go. In last chapter, we were talking about moving average. As I said, moving average is not that useful in terms of forecasting, but it is useful in terms of removing seasonality or as an intermediate step. Now let's take a look at an example and see how we can tease out each component and then put them together. So in this example, it says Perkin Kendall, the analyst for the Costco Marine Corporation, used auto-correlation analysis to determine that sales were seasonal on a quarterly basis. Now he uses decomposition to understand the quarterly sales variables and to predict for future period. On the right-hand side, in this table, you can see the original data, which is sales, together with all the individual components. T stands for the trend, S stands for the seasonality, C stands for the cyclical component, and I stands for the irregular, okay? So this data is quarterly data starting from 2000 to 2006, a total of 28 observations. So let's examine the data briefly, although the question already tells us there is seasonality on a quarterly basis. Down here, you can see the time series plot of the sales. I don't observe trend very clearly. It seems like it is not moving upwards, maybe a little bit towards the end, but I do see very strong seasonality. That is, the same pattern repeats itself every 4 quarters. Within the table, within the graph for the autocorrelation, we can see clearly that for lag 4, the autocorrelation coefficient is significant and it's much bigger than the lag before it and then the lag after it. So now we confirmed seasonality from the data. Let's see how we can do the decomposition. We're gonna take the second observation as example, and I want to go through the steps to show you how each number is calculated. This hopefully can help you better understand how we really can take out each component from just probably 28 numbers in the data, right? If you look at the 28 numbers out there, you may see some general pattern and the number is getting kind of larger towards the end, but nothing else. So the steps will tell you how we identify each component. And for this example, we're gonna do the multiplicative model. Going backwards, remember that we have 2 models. One is the additive and the other one is the multiplicative. For this particular example, I decided to do the multiplicative really because I do see the variation changes across time. At the beginning and towards the end, the variation is relatively smaller and the variation in the middle is larger. And therefore, additive model may not be a good choice. All right, there are a total of 7 steps. In the first step, we want to identify the first component, the trend. We're gonna use the regression to obtain the trend line, or you can do the trend analysis to obtain the same trend line. It's basically a straight line and the equation is given as t equal to 361.24 plus 0.79 times the time t. Okay, and since we're focusing on the second observation, the small t will be taking a value of 2. And we replace the small t with 2 in the equation to get the trend prediction, which is 262.759. So that's the trend component and the prediction using the trend line. In the next step, now we are ready to remove the trend from the data, okay? If you look at the original model, right? So the actual value of sales is equal to each component multiplied. So if we want to remove the trend component, we will need to use the actual value of sales divided by the trend, which is 262.79. And that's what we did here. Y divided by T, plug in the numbers, the result is 1.177. And we label that as SIC. It's not any fancy term. It just stands for seasonality, cyclical, irregular, just the rest of the 3 components combined, right? Because after we take away trend, we'll have these 3 components left. In the next step, we're gonna identify the seasonality. As I mentioned, we're gonna use the seasonal index to capture the seasonality. And again, we didn't go through the process of getting the index, just rest assured Minitab will report the seasonal index for all seasons. Now, in terms of our particular example, for the second quarter, the seasonal index is 0.78. And then we can use this seasonal index to remove the seasonality. If we use the actual Y, the actual sales, divided by the seasonality, we take away the seasonal component, right? So as you recognize, we do division. Going through the calculation, the result is 304.434. And we are only taking away the seasonality. Okay, and therefore we still have trend, cyclical, irregular left, 3 components. And the reason I added this step instead of going to the next one, because in the next one, we can take away trend and seasonality at the same time. The reason I added this step is to show you how we can remove seasonality and how to get these seasonally adjusted data. When we move to regression, you're gonna start working on the third part of the project. And there, you're gonna use the macroeconomic data. When you open the macroeconomic data, you will find that for all of the variables there are raw data, there's also the seasonally adjusted data. Now you know how the seasonal is removed or how the data is adjusted for season. So moving to the next step, here's the step where we take away both the trend and the seasonal component. Then we have only the cyclical and irregular components left. So it's denoted by CI, and it's equal to the original data divided by both the trend and the seasonality. So we just plug in the numbers. Original data is 309.2. Trend is 262.759. And so going through the calculation, the final result is 1.159. Now that we only have the cyclical and irregular component left, we will try to separate these two, all right? So here we go. We're using the moving average method to identify the cyclical. So as I said, moving average is really a good tool for the forecasting itself, but rather an intermediate step for some more advanced techniques. When we use moving average for the CI component, we are basically averaging out the random error or the irregular. And what we have left is really the cyclical component. We use the 3-period moving average, meaning we're adding 3 numbers up and divide by 3. So for the second observation, we added the first 3 quarter sales and then divided by 3. The cyclical component turns to be 1.118. Now I want to point out that sometimes when we calculate the average of the 3-period, we usually record the results for the 3rd period. But for the decomposition we have here, what we're doing is we're recording the average at the center, okay? So we're recording the average for the 2nd period. All right, now by step 6, actually, we pretty much have every item. In number 6, what we do is just take away the cyclical, then we have the irregular left. So the irregular is equal to whatever left for CI, which is 1.1959 back here, divided by the cyclical component 1.18, and I guess I didn't bother to write the answer, which is 1.036. All right, so then after these steps, if we want to predict for a future period, what we do is we predict for the trend by replacing t with the appropriate number. We calculate the seasonal component based on the seasonal index. Then we calculate the cyclical component together with the irregular and multiply each component together. We will get the forecast for any period in the future, as well as for the periods included in the data. All right. So that's an example with the multiplicative model. For additive model, really nothing special. We do the same steps. The difference is we're gonna replace division with subtraction. And of course, by the end, when we want to put them together, instead of multiplying components, we're adding the components, okay? So these are the steps. Now we obtained every number listed on the table. And I want to move back to the original complete table and point out a few things. So when we identify the trend and take the trend away from the data, we call this column, what I'm trying to circle now, we call that detrended data. Okay, so this is called detrended data, right? And then when we remove seasonality from the data, okay, we've got TCI left. So the other column I'm trying to highlight there, this is called the seasonally adjusted data. All right. All right, so, and And finally, this column CI, meaning that we removed both the trend and the seasonality, the last column I'm trying to highlight up there. Hopefully I have enough space to type. This is called detrended and seasonally adjusted data. All right, now we are ready to take a look at the Minitab and see how we can carry out the analysis within Minitab. Let me move over to Minitab and we'll go from there. So I've already opened the data file, which is named as Coastal Marine Corporation. We had another data file for the same company, but with that file, I also labeled with chapters 3. So this is a separate file, and we only have one column for the sales. So we'll go to Stat, Time Series, and choose Decomposition right below Trend Analysis. And the variable is sales. We need to define the seasonal length, which is 4 because it is quarterly data. We will use the multiplicative model as we've determined earlier, and we will also incorporate trend plus seasonal. Although we wasn't able to quite confirm the trend, it is safer to include it just in case there is trend there. We would also like to store some of the results to see how we obtain the values in the big table with the Minitab analysis. So click on Storage, and we want to select detrended data, seasonals, seasonally adjusted data, as well as residuals, because we eventually want to check the residuals to see if the model is adequate or not. So click OK. And OK again. There we go. The summary of the model we have is multiplicative model. The data sales with 28 observations. We also see the trend line, which is the same trend line when we do trend analysis earlier. And below that, we will see the seasonal indices. This indices will have more explanation later on. And the accuracy measures, the focusing area are reported in this box. Right below that, you will see the graph showing the original data and the forecast using the decomposition model. The result also show 4 more graphs, which are original data, detrended data, seasonally adjusted data, seasonally adjusted and detrended data. Okay, so if we want to check on the residuals, we will go to Stat, Time Series. We will get the time series plot for the residue as well as the autocorrelation for the residue, and the variable will be residual 1. So before we return to PowerPoint for further discussion, I just want to point out what is going on with these couple of extra columns reported after we conduct the analysis. C2 here is what we call the detrended data. So it's basically the original data divided by the prediction using the trend line. We actually did this for the second observation earlier. And C3 is the seasonal indices actually. So if I pull a little bit, you can compare, right? So these 4 numbers repeat all the way down to the end, and they are just the 4 seasonal indices we saw in this table. And this column C4, the notation is a little bit confusing, but it's actually reporting the seasonally adjusted data, okay? It's not detrended, seasonally adjusted, it's just seasonally adjusted data. And in the last column, we have the residues. Minitab, without us asking for this column, will just calculate these values behind the scene, report the final results in this window. All right, so we're gonna move back to PowerPoint to continue our discussion. So on this page, as it showed how to, just showed how to conduct the decomposition analysis, as well as getting the extra data we wanted. And results are shown here. And I want to highlight a few notes about the seasonal indices, okay? The seasonal indices will be around 1, some will be above 1, some will be below 1. So a seasonal index is 1 basically means for that season, the sales is equal to the average of the 4 quarters. And if you see an index smaller than 1, that means sales in that quarter are usually lower than average, below average. With indices higher than 1, that means for those quarters, sales are usually above average, okay? And of course, the bigger the number, the higher the sales is above the average. So the seasonal indices will allow us to identify which season is a good season, which season is a slow season. Apparently, for our example here, we see season 3 and season 4 are good ones. Season 1 is the low season. That actually, just recognize, that's a typo up there. It should be 1, so it should be season 1. On the PowerPoint slide you printed from D to L, this should have been corrected. So here are the graphical representation of the data we obtained later. We have the original data, time series plot. We also have the time series plot of the detrended data. If you compare the detrended data with the original data, actually we don't see much difference. There's slight difference, but not that much. It just implies 2 things. Number 1, maybe there's no trend. Number 2, maybe the linear trend is not the right way to do so. Now, if we move to the third graph, seasonally adjusted data, what we would observe is we get rid of the seasonality. What we have should be the trend plus the cyclical component plus the irregular. And even with the seasonally adjusted data, I don't really see a linear trend. I don't see a straight line. I do see roughly a curve, kind of like that. And lastly, for the seasonally adjusted and detrended data, seems like the data is to a certain extent random. I don't see a lot of pattern there. In terms of cyclical trend, maybe there is some going like this waves. Next, we will check on the residues, right, to see if the model is adequate or not. So I obtained the time series of plot and also the autocorrelation function. From the time series plot, honestly, I didn't notice that anything unusual. I didn't see any pattern. However, the good thing about using ACF is that visually, if I can't identify anything, ACF will be able to capture that. So if you look at the ACF function on the right-hand side, first of all, the first leg is significant. Definitely means something. At least the model is not adequate to capture that significance. Second, the lags, the autocorrelation does decline gradually. So that still shows certain pattern. And this just suggests the decomposition model we just used may not be adequate, right? We may need to consider other models The other thought I would have is that since when we were looking at the component analysis, we recognize that there might be a trend that is a curve instead of a linear trend. And since for the decomposition carried out, we only consider linear trend, that might be the reason for this significant autocorrelation in the residual. So suggesting maybe we should try some other trend than the linear trend. However, within Minitab, if we just rely on the buttons to conduct the analysis, we are not able to change the trend. So either we will need to rely on other models or rely on more advanced techniques to incorporate non-linear trend in decomposition. But that's really beyond the scope of our discussion. Although we identified some potential issues with the decomposition model we just fitted, for illustration purpose, I want to show you how we use that model to do a forecast. So we're gonna do the forecast manually, and then we will move to Minitab, use Minitab to do the forecast for us. We used a multiplicative model that is for all the components to be multiplied together. So to do the forecast manually, we will need to forecast for each component, the T, the S, C, and I, and then multiply the four of them together to get the overall forecast. We know the trend from the model, it's given here. We also know the seasonal indices given in this table. So we are ready for this task. A couple of steps listed here. The first step is to do the forecast using the trend. So since we have 28 observations, we're gonna do T equal to 29, which is 28 plus 1, because we're doing one step ahead forecast. And therefore, the capital T, which is the trend, is calculated to be 283.251. Basically, we're replacing the lowercase t with 29 to get the results. Okay, in step 2, we're gonna use the seasonal index to calculate the seasonal component. So seasonal index is 0.77967. Since one step ahead forecast will be the first quarter in 2007. So that's the seasonal component. Now for cyclical and irregular, these two are a little bit tricky. We can never ever forecast irregular since it's random. So usually we would assume irregular to be 1 for a multiplicative model. For cyclical, it depends. If we don't expect anything extraordinary happen in the upcoming year or period, we will also assume the cyclical to be 1, meaning business as usual, nothing special happens. Sometimes we can use the forecast for the macroeconomic variables as the cyclical, because basically cyclical are the up and downs due to the overall economic environment. And if we can predict the economy to be going to a certain direction, we can use that as the cyclical prediction. So for our case here, we're gonna just assume the cyclical and irregular are both 1. All right, and finally, for the last step, we just multiply all items together. The trend is forecast to be 283.251, multiplied by the seasonal index, 0.77967, and cyclical and irregular are both 1. So our overall forecast is 220.842. And that's what we do manually. By the way, what if we have a model that is additive? Well, the steps will be similar. We still forecast for each item, but at the end, we would add all 4 components up. In addition, for additive model, we're gonna assume the cyclical and irregular to be 0. Okay, that's the big difference. For multiplication, we can't assume these two to be 0 because the overall results will be 0. When you do multiplication, basically you are scaling numbers. But when we do addition, we want to assume the cyclical and irregular to be 0 because these two remain the same. All right. Now, next, we can use Minitab to do the forecast for us, which will be much easier because we do not need to go through the steps. I do want to move to Minitab and show you how we do the forecast in decomposition. Nothing special there, it's easy as click. I would also like to show there the two graphs we obtained for checking the residuals. These are all something we did before, but just for practice purpose, I want to do that one more time. So let me head over to Minitab. So here we go. That's the Minitab we had before we switched to PowerPoint slides. Let me show you the residual checking first. So we have the residual listed in column 5. And we want the time series plot for that as well as the ACF graph. So we'll go to Stat, Time Series, and pick Time Series Plot. Click OK. The variable will be residuals, residual 1, and then click OK to get the graph for the residual time series plot. We also want the autocorrelation, so stat time series, autocorrelation, variable is residue. We're gonna leave the default number of legs, click OK. There we have the ACF graph. All right, so in terms of forecast, usually we do that after we specify the model and determine that is the model we want to use. So we have to re-estimate the model by going back to stat, time series, decomposition, the variable sales, seasonal that is 4, everything stays the same. We just need to generate forecast. Let's do it for 1 full year. So I'm gonna to put number of forecast as 4. And then I click OK. And notice earlier I checked on the storage. This time these will appear one more time. No big deal, but you have 4 more extra columns, which are exactly the same as the previous 4. But this time we do see the forecast and they are listed in this table. They're also included in this graph. All right, so now we are ready to move back to the PowerPoint slides and continue our discussion. So there we go, that's the graph for the forecasts from Minitab. What we can see is that the forecast value is given by this purple curve and purple dots. They show the same pattern as the previous year. We also see the overall trend, which means the overall revenue is increasing from year to year. The new forecast for 2007 also showed slightly higher values in comparison with the previous year, which makes sense to us. All right, I have 2 more notes to show you why decomposition actually turns to be important in economic forecasting, not just for forecasting for future period. It is also because some of the techniques used within decomposition are useful for other purpose. So first one is about seasonally adjusted data. Right. So as I mentioned, for the macroeconomic variable that you will be using later on, you will see the series to show the raw data and the seasonally adjusted data. For most economic series published by the Federal Reserve, they do provide seasonally adjusted data so that for the public or for the researchers, we can easily see the trend. And there are situations where we are more interested in the general pattern than the seasonal variations. Sometimes the seasonal variation may interfere with identifying the general pattern, and therefore we need to remove it. All right, we've already done this. We are able to obtain the seasonally adjusted data. And here are just a few advantages that we've already mentioned. If you do a seasonal adjustment, we can reliably compare values at different points in time. So for example, if I want to compare the third quarter of 2000 with the second quarter of 1998, right? It's different quarters. If I don't remove the seasonality, I can't compare them reliably. However, if I remove seasonality, I will be able to compare different quarters in different years. Once the seasonal variation is removed from the data in terms of running regression or other analysis, it's easier to understand and identify the relationship between economic or business variables. And as you've seen, it can be also helpful and useful in forecasting. So the second note is related to business indicators, okay? Business indicators are also important because for time series data, whenever there's cyclical trend in it, we want to identify the cyclical trend, but we also understand that the cyclical component is related to the macroeconomic condition where the business run, in which the business run. So in terms of predicting what will happen in the future as to the macroeconomic environment, we also want to do the forecast for cyclical, right? For cyclical, we can't predict within the model because that depends on the overall economic condition. So if we want to predict for the cyclical, then we would need to ask, what is coming up in the next couple of years? And that kind of depends on where we are now, right? So if we are in a recession and we see things improving gradually, we know we are heading to recovery. And if we see things are going down and getting worse and worse, then we know things are getting bad. We are falling into maybe a recession. So in economics, the researchers have been debating and researching for what we call leading indicators or business indicators to help us to try to determine and predict what would happen next. The current list include 10 leading indicators, meaning that those indicators will give us an alert ahead of time that economic recession is coming up. And there are 4 coincident indicators, means those indicators will change together with the overall economic condition. And finally, there are 7 lagging indicators, meaning that those indicators will change only after the macroeconomic condition changed. All right, so let's just take a look at the leading indicators briefly, because usually these are the indicators that we're more interested. They give us a heads up. They include building permits, and this suggests how the housing market is doing. An index of stock prices. The stock market apparently is a very important signal as to the economy. And these indicators are published by Survey of Current Business monthly. There are more indicators that I didn't list there. All right, for coincident indicators, we have industrial production, we have manufacturing, and trade sales. And for the lagging, we have prime interest rate and unemployment rate. So these two will come after the economy changes. All right, so that's all we have for this lecture. All right, so that's all I have for this lecture. Let me know if you have any questions.